At the end of this video, you should be able to explain how a main sequence star generates energy, and describe the evolution of a star after its main sequence stage. Chapter 30, Section 2, the main sequence stage. The second and longest stage in the life of a star is the main sequence stage. During this stage, energy continues to be generated in the core of the star as hydrogen fuses into helium. Fusion releases enormous amounts of energy. For example, when only 1 gram of hydrogen is converted into helium, the energy released could keep a 100-watt light bulb burning for more than 200 years. A star that has a mass about the same as the Sun's mass stays on the main sequence for about 10 billion years. More massive stars, on the other hand, fuse hydrogen so rapidly that they may stay on the main sequence for only 10 million years. Because the universe is about 14 billion years old, massive stars that formed long ago have long since left the main sequence. Less massive stars, which are at the bottom right of the main sequence on the HR diagram, are thought to be able to exist for hundreds of billions of years. The stages in the life of a star cover an enormous period of time. Scientists estimate that over a period of almost 5 billion years, the Sun, shown in Figure 4 or on the screen here, has converted only 5% of its original hydrogen nuclei into helium nuclei. After another 5 billion years, though, with 10% of the Sun's original hydrogen converted, fusion will stop in the core. When fusion stops, the Sun's temperature and luminosity will change, and the Sun will move off the main sequence. Leaving the main sequence. A star enters its third stage when almost all the hydrogen atoms within its core have fused into helium atoms. Without hydrogen for fuel, the core of a star contracts under the force of its own gravity. This contraction increases the temperature in the core. As the helium core becomes hotter, it transfers energy into a thin shell of hydrogen surrounding the core. This energy causes hydrogen fusion to continue in the shell of gas. The ongoing fusion of hydrogen radiates energy outward, which causes the outer shell of the star to expand greatly. Giant stars. A star's shell of gases grows cooler as it expands. As the gases in the outer shell become cooler, they begin to glow a reddish color. These large red stars are known as giants. Because of their large surface areas, giant stars are bright. Giants, such as the star Arcturus, shown in Figure 5 or on the screen here, are 10 or more times larger than the Sun. Stars that contain about as much mass as the Sun will become giants. As they become larger, more luminous, and cooler, they move off the main sequence. Giant stars are above the main sequence on the HR diagram. Supergiants. Main sequence stars that are more massive than the Sun will become larger than giants in their third stage. These highly luminous stars are called supergiants. These stars appear along the top of the HR diagram. Supergiants are often at least 100 times larger than the Sun. Betelgeuse, the large orange-red star shown in Figure 6 on the screen here, is one example of a supergiant. Located in the constellation Orion, Betelgeuse is 1,000 times larger than the Sun. Though such supergiant stars may make up only a small fraction of all stars in the sky, their high luminosity makes the stars easy to find in a visual scan of the night sky. However, despite the high luminosity of supergiants, their surfaces are relatively cool. The final stages of a Sun-like star. In the evolution of a medium-sized star, fusion in the core will stop after the helium atoms have fused into carbon and oxygen. With energy no longer available from fusion, the star enters its final stages. Planetary Nebulas. As the star's outer gases drift away, the remaining core heats these expanding gases. The gases appear as a planetary nebula, or cloud of gas that forms around a sun-like star that is dying. Some of these clouds may form a simple sphere or ring around the star. However, many planetary nebulas form more complex shapes. For example, the Ant Nebula has a double-lobed shape, as is shown in Figure 7 or on the screen here. White dwarfs. As a planetary nebula disperses, gravity causes the remaining matter in the star to collapse inward. The matter collapses until it cannot be pressed further together. A hot, extremely dense core of matter, a white dwarf, is left. White dwarfs shine for billions of years before they cool completely. White dwarfs are in the lower left of the HR diagram. They are hot but dim. These stars are very small, about the size of Earth. As white dwarfs cool, they become fainter. This is the final stage in the life cycle of many stars. When a white dwarf no longer gives off light, the star will become a black dwarf. However, this process is long, and many astronomers do not believe that any black dwarf stars yet exist. Novas and supernovas. Some white dwarf stars are part of a binary star system. If a white dwarf revolves around a red giant, the gravity of the very dense white dwarf may capture gases from the red giant. As these gases accumulate on the surface of the white dwarf, pressure begins to build up. This pressure may cause large explosions, which release energy and stellar material into space. Such an explosion is called a nova. A nova may cause a star to become many thousands of times brighter than it normally is. However, within days, the nova begins to fade to its normal brightness. Because these explosions rarely disrupt the stability of binary stars, the process may start again and the white dwarf may become a nova several times. A star in a binary system may also become a supernova, a star that has such a tremendous explosion that it blows itself apart. Unlike an ordinary nova, a white dwarf can sometimes accumulate so much mass on its surface that gravity overwhelms the outward pressure. The star collapses and becomes so dense that the outer layers rebound and explode outward. Supernovas are thousands of times more violent than novas. The explosions of supernovas completely destroy the white dwarf star and may destroy much of the red giant. The final stages of massive stars. Stars that have masses of more than 8 times the mass of the Sun may produce supernovas without needing a secondary star to fuel them. In 1054, Chinese astronomers saw a supernova so bright that it was seen during the day for more than 3 weeks. At its peak, the supernova radiated an amount of energy that was equal to the output of 400 million suns. Supernovas in massive stars. While only a small percentage of white dwarfs become supernovas, massive stars become supernovas as part of their life cycle, which is shown in Figure 8 on the screen here. After the supergiant stage, these stars contract with a gravitational force that is much greater than that of small mass stars. The collapse produces such high pressures and temperatures that nuclear fusion begins again. This time, carbon atoms in the core of the star fuse into heavier elements such as oxygen, magnesium, or silicon. Fusion continues until the core is almost entirely made of iron. Because iron has a very stable nuclear structure, fusion of iron into heavier elements takes energy from the star rather than giving off energy. Having used up its supply of fuel, the core begins to collapse under its own gravity. Energy released as the core collapses is transferred to the outer layers of the star, which explode outward with tremendous force. Within a few minutes, the energy released by the supernova may surpass the amount of energy radiated by a sun-like star over its entire lifetime. Neutron stars. Stars that contain about 8 or more times the mass of the Sun do not become white dwarfs. After a star explodes as a supernova, the core may contract into a very small but incredibly dense ball of neutrons called a neutron star. A single teaspoon of matter from a neutron star would weigh 100 million metric tons on Earth. A neutron star that has more mass than the Sun may have a diameter of only about 20 kilometers, but may emit the same amount of energy as 100,000 suns. Neutron stars rotate very rapidly. Here is a table of information that should be noted. Pulsars. Some neutron stars emit a beam of radio waves that sweeps across space, like a lighthouse light beam sweeps across the water. Because we detect pulses of radio waves every time the beam sweeps by the Earth, these stars are called pulsars. For each pulse we detect, we know that the star has rotated within that period. Newly formed pulsars, such as the one shown in Figure 9 on the screen here, are commonly surrounded by the remnants of a supernova. But most known pulsars are so old that these remnants have long since dispersed and have left behind only the spinning star. Black holes. Some massive stars produce leftovers too massive to become stable neutron stars. If the remaining core of the star contains more than 3 times the mass of the Sun, the star may contract further under its greater gravity. The force of the contraction crushes the dense core of the star and leaves a black hole. The gravity of a black hole is so great that nothing, not even light, can escape it. Because black holes do not give off light, locating them is difficult. But a black hole can be observed by its effects on a companion star. Matter from the companion star is pulled into the black hole. Just before the matter is absorbed, it swirls around the black hole. This gas becomes so hot that X-rays are released. Astronomers locate black holes by detecting these X-rays. Scientists then try to find the mass of the object that is affecting the companion star. Astronomers conclude that a black hole exists only if the companion star's motion shows that a massive, invisible object is present nearby. At this point, you should be able to explain how a main sequence star generates energy, and describe the evolution of a star after its main sequence stage.